The signal vanished 49 seconds early. Mars Climate Orbiter appeared healthy. Its orbit insertion engine started on time. The spacecraft was following commands. The path beneath it was wrong. Post-loss estimates put its closest approach at 57 kilometers, an altitude the investigation judged too low to survive. The error began on Earth, in a ground software handoff, producing unexplained discrepancies for months. Mars Climate Orbiter launched on the 11th of December 1998. Its job was to study the Martian climate from orbit and relay communications for Mars's polar lander and future missions. But before the science could begin, navigation had to place the orbiter on a precise path past Mars. The target for its first periapsis, the lowest point of that first orbit, was 226 kilometers above the planet. On the 23rd of September 1999, the main engine began the orbit insertion burn at 9 hours and 46 seconds UTC. The engine was not suffering from a hidden English versus metric command. The mismatch that doomed the navigation solution involved much smaller thruster firings recorded by software on the ground. A spacecraft uses reaction wheels to turn and hold its orientation. As those wheels accumulate momentum, small thrusters fire to unload them. The process is called angular momentum desaturation, or AMD. Each firing gives the spacecraft a tiny push. Ground navigators need the size of that push, because even a small, unmodeled change in velocity can grow into a large position error over an interplanetary cruise. Before launch, navigation accuracy work assumed roughly one AMD event every 5 to 7 days. In flight, they occurred about twice a day. The handoff carrying those small force measurements therefore mattered far more often than the original analysis assumed. The JPL review board calculated that without any cruise corrections, the mismodeling could have produced more than 10,000 kilometers of error at Mars. That is a counterfactual, not the spacecraft's actual misdistance. 4 trajectory correction maneuvers removed most of the accumulated error. After the 4th, the remaining discrepancy was still 169 kilometers. The ground file that described those impulses was called SM forces. The controlling software interface specification required each impulse in Newton seconds. A lower-level requirement did not restate the unit, and an equation kept in a development folder produced the value in pound force seconds. The number crossed the interface without being converted. Navigation software read it as Newton seconds. Because 1 pound force is about 4.45 newtons, the ground model understated the effect of every recorded firing by a factor of 4.45. This was not an onboard computer error, and it was not the main engine using the wrong unit. It was a ground software output violating a documented interface. The mishap board identified that mismatch as the root cause. The required unit had been written down. Walkthroughs and unit tests did not expose the mismatch, and no effective end-to-end interface test proved that the value produced on one side meant the same thing when the navigation system consumed it. That explains how the ground trajectory became wrong. It does not yet explain why the mission reached Mars with the error still alive. Within 2 days of launch, the teams found a different problem in the same data handoff. The AMD file's format and coordinate convention were incompatible with the navigation software. That defect was verified corrected on April 19, and navigation could read the file on April 26. The format problem and the unit problem were separate. Fixing the first made the file readable. It did not make the impulse values correct. On April 26, navigation also reported that Doppler tracking showed velocity changes several times larger than the values in the AMD file. That was evidence that the model and the observed motion did not agree. It was not yet a diagnosis of the unit mismatch. No formal anomaly report was written. The cross-team investigation did not resolve the discrepancy. A request to elevate the issue was declined, and a June reorganization broke continuity in the work. By August, navigation solutions were scattering more widely. This is why NASA ignored warnings is too blunt. The record does not show a team knowingly accepting the pound-for-second error. It shows a real discrepancy being handled informally, passed between groups, and never converted into a durable, owned anomaly that survived changes in people and organization. The clue existed. The system around the clue did not force an answer. The changing approach estimates show the cost of that unresolved adapt. The targeted first periapsis was 226 kilometers. 2 days before orbit insertion, the last estimate was 150. A solution calculated about 2 hours before insertion predicted 110. Only after contact was lost, with the small force error corrected, did the board calculate 57 kilometers. Those numbers are not a live countdown of the spacecraft falling toward Mars. They are separate navigation solutions, produced at different times from different tracking data cutoffs. The spacecraft itself continued to look nominal. At 9 hours, 4 minutes, and 52 seconds UTC, its radio signal disappeared behind Mars, 49 seconds earlier than the ground prediction expected. The early cutoff revealed that the geometry, not the telemetry status, had been telling the more dangerous story. By then, the final chance to change that geometry had already passed. There had been a fifth trajectory correction maneuver under discussion. A TCM-5 command sequence was built and run through a simulator without problems. But simulator success was only one part of readiness. TCM-5 had not been included in the baseline mission timeline or the operational readiness testing. Review, criteria, and shared decision preparation were incomplete. At a limited review on September 18, navigation was not represented. The group concurred with a tentative no-go, and TCM-5 was not performed. The Phase I board counted that non-execution as one contributing cause. The JPL board said that if MOVEit raised the 57-kilometer path to perhaps 100 kilometers, survival was possible. Possible is not certain. The reports do not prove that TCM-5 would have saved the spacecraft, and they do not show that no sequence existed. They show something more useful. A technical option can exist without the operational preparation needed to judge and execute it safely when the clock is running out. The Phase I investigation did not stop at the unit mismatch. Beyond that root cause, it listed 8 contributing causes. The velocity change mismodeling went undetected. The operations team was not sufficiently familiar with the spacecraft. TCM-5 was not performed. Systems engineering was inadequate in the transition from development to operations. Communication between project elements was inadequate. Navigation staffing was inadequate. Training was inadequate. And the ground software did not receive adequate verification and validation. These were not 8 separate root causes, and the board did not say each one independently doomed the mission. Together, they described the holes in a safety net. Some safeguards should have detected the defect: requirements tracing, software verification, and an end-to-end interface test. Others should have helped people interpret the discrepancy: training, spacecraft familiarity, and adequate navigation staffing. Systems, engineering, and communication should have kept the issue owned across organizational boundaries. Contingency preparation should have made the final correction a better informed decision. The ruin mechanics reading, grounded in those findings, is that this mission was not lost merely because 2 groups preferred different unit systems. A specified interface was violated, and the surrounding safeguards failed to catch the error, explain the evidence, preserve responsibility, or recover in time. The Phase II board then widened the frame beyond the immediate technical teams. It found that significant resource reductions had not been matched by enough process discipline, risk management, or emphasis on mission success. It also judged that project leadership had focused too heavily on cost and schedule relative to risk. That is an attributed finding, not a claim that every attempt to build a mission faster or cheaper must fail. It explains why a correct line in a specification was not, by itself, protection. A requirement protects a mission only when the organization can enforce it. When staffing is sufficient, developers and operators share the same model of the system, interfaces are tested as interfaces, discrepancies become owned anomalies, and recovery options are prepared before they are needed. On Mars Climate Orbiter, the document said Newton seconds. The working system still allowed pound-force seconds to pass. What vanished at 9 hours, 4 minutes, and 52 seconds was the signal. What was unquestionably lost was the mission. The corrected 57-kilometer estimate was judged too low for survival, but no impact was observed. The Phase 1 report allowed more than one physical outcome: destruction in the atmosphere or escape onto a path around the Sunday. The exact fate remains uncertain. The failure mechanism does not. The wrong trajectory survived because a bad value crossed an inadequately verified interface. Observations that challenged the model never became a resolved, durable anomaly. Organizational continuity broke, and the last recovery option was not operationally mature enough to overcome that uncertainty. Mars Climate Orbiter appeared healthy because the spacecraft could execute its commands while the ground navigation picture of its path was wrong. 49 seconds early, Mars exposed the difference. The orbiter was also meant to relay data for Mars' polar lander. That makes the lander more than a footnote. Its mechanism is the next question. For this mission, the lesson is already complete. A correct specification is only a safeguard when the system proves it was followed. As always, thanks for watching. If you enjoyed this video, feel free to subscribe. I'll see you in the next one.